Section 6.2 deals with the collision theory, but we're not talking about that type of collision. We're dealing with collisions of atoms. So collisions we know must occur for a reaction to take place. If I have atoms and they're not even near one another, they're not going to be able to form something new. They have to hit each other first. The electron clouds are going to want to repel one another. We know that those negatives are going to want to go as far away from one another as possible. So we have to have enough kinetic energy for those electron cloud repulsions to be counteracted and for them to actually collide. So a little refresher here, we talked about physics a teeny tiny bit being kinetic energy as the energy of motion. We were using the word speed quite a bit for this. But we know that there's also a minimum amount of energy required to break and make bonds. We saw that in Chapter 5 when we were dealing with the energy diagrams, that little bump, the hill that we had to overcome, and we called that activation energy. So activation energy is the minimum amount of energy required for a reaction to take place. The symbol that we use is a capital E with a subscripted lowercase a. So we know E for energy. We've used that one quite a bit before. And the A is just saying, hey, it's not just any old energy, it's the activation energy. And the unit that we use for it is the same as all of the energy units that we've used before, kilojoules per mole. It's going to change for the reactions. Some require much less energy for the reaction to occur than other reactions. So we're going to have to be specific about what equation we're talking about. And here's just one of those energy level diagrams. That hill that we're dealing with is that activation energy. We also have to worry about steric factors, and that is how they are oriented. So the molecules must also be oriented correctly for them to be able to bond. It's most important for very large molecules, especially large organic molecules, as they come towards one another, whether or not they will react. The larger they are, the more important it is for us to get in the right orientation. And here's just an image from online of some ineffective ways of hitting and an effective way where they have collided. They've collided with enough energy and in the right orientation. We can increase the rate of a reaction in multiple ways. The main thing that we're thinking of on the molecular level is that we increase the rate by increasing how frequently we have collisions, because the more times we collide, the more likely it'll be in the correct orientation and with the correct amount of energy. So things that we can do, we can increase the concentration. That's because we're going to have more of the atoms there that they can interact with one another. So increasing concentration would increase the collision frequency. Also, increasing pressure if we're dealing with a gas. This is because by increasing pressure, we're most likely decreasing the volume. So it's thinking of concentration in a slightly different way. We kind of have more concentration if we have a smaller volume and greater pressure, which means that they're going to collide more frequently, which means we're going to increase that rate. Also, if we have a solid, we can increase the surface area of the solid, like by pulverizing them and making the particles smaller, and that's because there's more places then for it to interact. Other things that we know will affect reaction rate include temperature, and that's increasing collisions as well. We weren't thinking of it necessarily that way before, but it will, because we're going to increase the velocity if we're increasing temperature. Remember, temperature is an average of the velocities of the molecules that are present. So that increase in temperature increases the velocity. If they're moving around more often, they're more likely to collide, and hopefully with that right amount of activation energy and with that right orientation. Another thing that we can do that would increase the reaction rate would be to add a catalyst. We know that that lowers the activation energy, which brings us here. So we increase the rate of a reaction without undergoing any permanent change. So that catalyst that I put in comes out in the same amount and as the same thing. The only thing it's done is lowered the activation energy. It's made it a shorter hill for me to have to run across, made it easier for me. Have a hill rather than a mountain to go over. So So we can take a look at this question. Which change of condition will decrease the rate of a reaction between excess zinc granules and dilute hydrochloric acid? Well, let's look at each of these bit by bit. If I increase the amount of zinc, that means I've got my same size beaker, mainly changing concentration there. I'm adding more of it to the solution. So if I add more of it, I'm increasing concentration. That's going to increase the rate. So that's not decreasing the rate. So it's not A. B, increasing the concentration. Bingo, we saw that again on the last slide. Increasing concentration is going to increase the rate of a reaction. There's more molecules there, so more likely going to have collisions in the correct orientation and with the correct activation energy. C, pulverizing the zinc granules. Haha, that is one of the keywords for our surface area. We've increased the surface area. There's more places for the hydrochloric acid to interact with the zinc. So that one is going to increase the rate of collisions, which means would increase the rate of the reaction as well. Finally, decreasing the temperature. Sure enough, that one's going to be our answer. If we decrease temperature, the particles are going to move more slowly, decreasing the rate at which they are colliding, which would decrease the rate of the reaction.